Hi everyone, welcome back to another episode of Wall in a Box, where we use our favorite desktop model to look at geotechnical concepts related to retaining walls. This time we're going to talk about a common method engineers use to improve soil conditions and construct retaining walls called Select Backfill Wedge. We will discuss the theory behind this approach and see what we can learn with my favorite visualization tool, Wall in a Box. Retaining walls are used to support earth and create a vertical change in elevation from the top to the bottom of the wall. It turns out that there is a large variation in how much pressure different types of soil put on the wall. In fact, the amount of pressure that the retained soil puts on the wall is the single most significant factor impacting design of the wall. So the soil type behind the wall is very important. As engineers, we can perform tests on a soil to determine its properties. One of these tests is called the direct shear test. Here, you can see one of the commercially available machines that is used to run this test. It puts different amount of weight on a sample and then measures how much force it takes to shear the soil. If we run a series of tests on the soil and plot the results on a graph, we can calculate the angle of internal friction for that soil. You might have heard engineers mention the phi angle of a soil. This is what they're talking about. Soils that have higher friction angles, such as sands and gravels, hold together better and resist shearing more than soils like silts and clays with lower friction angles. Soils can be complex, so let's simplify things by ignoring cohesion and different unit weights of the soil, and let's just consider the effects of the soil's friction angle. As we mentioned, sands and gravels have a higher friction angle than silts and clays. They hold together better, and they put less pressure on the retaining wall than weaker soils. Now, if engineers could choose what soils are on a particular site, we would choose sands and gravels for sites where we want to build walls. Unfortunately, we don't get to make that choice. And there are plenty of times where we need to design and build retaining walls on sites with low-strength soils. One approach that engineers use to design walls to support weaker soils is to dig some of the existing soil out and replace it with stronger soils that have a higher friction angle. The idea is that if you dig out enough of the weaker material and replace it with something stronger, you will get to the point where the wall is no longer impacted by the weaker material. In an extreme example, let's pretend that you want to build a 10-foot high wall. If you dig out all the soil behind the wall for 50 or 100 feet and replaced it with a stronger soil, the wall probably wouldn't know there was anything behind it but the stronger soil. The weaker soil way behind the wall wouldn't have any impact on the wall. Of course, this example is extreme, and it's an extreme to make a point. I can't imagine anyone replacing that much material just to build a wall. The challenge for engineers is to determine how much soil we do need to remove to have the same type of effect. To define this point, many engineers start by considering the strength of soils where the failure plane would form behind the wall. A common approach is to start a little bit behind the wall and excavate at a 1-to-1 slope or flatter. The wedge of soil removed is replaced with a wedge of select fill, such as crushed stone or gravel. One of the earliest references I found for this approach is contained in a USDA Soil Conservation Service Engineering Field Manual from 1990. Using Wall in a Box, we can take a look at a few different wall sections and see what we can learn about how a select backfill wedge might impact a wall. For the first wall, let's look at a 6-block high wall with 2 different width blocks. For the backfill, we used plastic dowels that are fairly slippery, and they do a pretty good job of modeling the behavior of soil with a lower effective angle of internal friction. When you remove the support, you can see a failure plane forming in the soil behind the wall, and the wall failing and sliding. For the next wall section, we used the same 6-block high wall. However, this time we replaced some of the plastic dowels behind the wall with wooden dowels that aren't quite as slippery. This is intended to model replacing a weaker soil with a wedge of stronger material. Now, when we remove the support, you can see that the wall remains stable and doesn't fail in sliding. For our last wall section, we want to see if we can cause a failure in the wall with a select backfill wedge. To accomplish this, we're going to build a taller wall. When we remove the support, you can see that the wall fails in overturning. If you look closely, you can see that the failure plane forms inside the select backfill wedge. The weaker soil, further back in the bank, doesn't seem to be impacting the wall. Pretty neat to see what happens when we use our understanding of engineering principles to change conditions that matter so that we can design better walls. Of course, it's important to do our homework. Make sure you have good soil data and consider multiple potential failure modes. Engineers will want to pay careful attention to global stability, especially along the interface between the native soil and the Select Backfill Wedge. We sure don't want to design a wall that seems stable, only to have a failure in the slope behind and/or below the wall. Then, when you've done a thorough job, you can have confidence in the wall you're designing. If you are interested in learning more about Select Backfill Wedge, earth pressure theory, or precast modular block walls, I invite you to download a copy of the Precast Modular Block Design Manual. And if you have questions about retaining walls for your next project, you can contact our civil engineering team. We are always happy to help folks understand how our PMB wall systems can help meet your specific needs. After all, we want you to design with confidence.